the vector A is 0, then it's just multiplied by a scalar, mass. So that right-hand side is 0. So then the sum of the forces has to be 0. So then, that first law looks like, you can kind of figure it out from the second law. And then the last law, the third law, is that for every action, there is an equal and opposite reaction. So when when I'm standing here, I am pushing with all of my weight on the ground, right? And the ground is pushing back with exactly the same force, so that we're perfectly in balance and I'm not accelerating at all, I'm just at rest. So, whenever you have collisions or stuff like that, you might want to think about Newton's third law to help you figure out what's going on in the problem. So we'll come back to these again and again and again. But these are just, things to keep in mind, especially Newton's second law. We'll spend a lot of time talking about that. All right, so we're going to jump right off with an example. And it has to do with vectors, right? So if you kind of go back in your mind, think vectors, right? So a force is just a vector. It has its own units, it's newtons, right? Is a common force that you'll be seeing. But it's just a vector. So we have 2 astronauts that are using jetpacks to push a 940 kilogram satellite towards the space shuttle. One astronaut pushes with a force of 26 newtons, the other with a force of 41 newtons at an angle of 52 degrees with respect to the first. Our goal is to find the magnitude and direction of the satellite's acceleration. But right now, just focus on the forces and that they're vectors, right? So yeah, their units might be a little weird, but they're just vectors. And I want to know, what is the direction of the resultant force? Is it along F1? Is it along F2? Is it along the sum of the two? Is it along the difference of the two? So even though it's a new type of problem, start off the same way. Draw a picture of what's happening. Because we'll keep working with the problem, so a picture will help out. What kind of picture are you drawing? Someone tell me how to draw this. I'll draw a satellite. I don't know exactly what a satellite looks like, but something like this maybe.
It's on my list.
There's people in NASA just want their job.
Yep. Perfect. Okay, hopefully you have a satellite, right? You could just draw your satellite as this. That's fine.
I drew a box.
Just a little dot, a little square, whatever. However you want to draw your satellite. But keep in mind, no matter how elaborate you draw your satellite, we're treating everything as point particles right now. So all that matters is its center of mass. So this is perfectly fine. A little dot is perfectly fine. Okay, so what's happening to this satellite?
Someone's pushing it.
Someone's pushing it. How do you want me to draw the push?
I said straight on, and then
Straight,
the person-
like this way? Or this way?
Where's your space shuttle?
I feel like one person should be on each wing, because that'd be about a 52 angle.
Okay, I just want the first one. How do you want me to draw the first push?
Oh.
This horizontal? Is that okay? It doesn't matter. Punchline is, it doesn't matter. You just gotta pick some way and commit to it, all right? So we'll say the first one, here's astronaut number 1, and they're gonna push that way. Okay, then how does astronaut 2 push? Now it matters direction, because relative to the first one.
In the same direction, but let's go like 52 degrees count.
In the same direction,
Yeah.
so he's, sitting right here,
Yeah.
and he's pushing like this.
No, he's pushing like
Oh, he's pushing at an angle. Good, very good. And what is the angle between the two?
that. He's
52 degrees. So I could draw, something here to make it easier. This is 52 degrees, right? Right, so this angle is 52 degrees, that angle is 52 degrees. Right? We have two lines crossing each other. Okay, so we got a good picture. And now I want to know, what is the resultant push? Right, so what direction do they push together?
Towards the shuttle.
What?
Towards the shuttle.
Towards the shuttle, okay. All right, so if I would just give you, right, so I'm going to draw my force vectors here in what would be a free body diagram. We'll talk about this more, but. So we have the push for the first one is this direction. The push from the second one looks something like this, and these are 52 degrees away from each other. The other one's kind of in between them, like the resultant is kind of in between. So if you could imagine, right, me and Theo are going to push on this chair. Right, here's our satellite. You and I are astronauts, right? So I'm pushing this way, right, and Theo is pushing this way at the same time, right? And when we both push, the chair is going to kind of go that way, like halfway in between, sort of, right? I mean, one of us might be stronger than the other.
Well, yeah.
Right, because one might be pushing at 26 newtons, the other one's pushing at 41. But, you know, it'll kind of be somewhere in between. All right? So you add them, right? Because it's what is, you know, my push plus Theo's push will give you the resultant push, you know, the total push that we're pushing on the satellite, right? So if we add these two vectors, we do that by connecting them tip to tail, right? So it would look, you know, something like, that's a curvy vector, but, you know, straight like that. And so your resultant vector would look something like that. So the resultant force of the two astronauts is just this, it has the direction of the sum, right? So you could imagine, you know, calculating this vector and then finding a unit vector, right, for like direction. You could do something like that. You could imagine that could be where we're going. We're not going to go there, but you could imagine it. All right, so it should be along the sum of them, is the direction that resultant force is. Okay, so I have a little handout to give you guys. And it just kind of lays out steps of solving problems for Newton's laws. And we'll go through it together, but this is just, you know, you can look at it at home. Okay, so in your handout it talks about problem-solving process, right? So step one, draw a picture. You've heard that before, right? So you draw a picture. You can then represent that item as a single point, right? Because we're not worried about extended features like turning and rotating, not yet, all right? So everything can shrink down to just a single point. And then we draw a free body diagram. So this would be like the picture that I'm drawing, right? So I drew, you know, the satellite, and then here's person one, here's person two, and here's how they're pushing. This would be the free body diagram before I started adding the vectors. You know, where I draw all of the forces acting on that point particle, right? So we have two forces, the push of astronaut 1 and the push of astronaut 2. So I just draw those two forces, and their tails are on that dot. Right, so even though here I kind of drew where the tips are kind of touching the satellite, because it kind of, I don't know, seemed like it went with the picture. It's kind of the vibe I was going for. But when you draw a free body diagram, the tails sit on the dot. So if you have two vectors that are going in the same direction, like let's say instead of at an angle of 52 degrees, they both push in the same direction, you would connect them like this. Right, so you're kind of adding them on, but the tail sits on the dot. Again, it's important to have a coordinate system. You know, in this case, we're worried about, you know, the direction of, you know, we were worried about the direction of motion. But, you know, coordinate system. And then you want to break things into x and y components, right? So you could say x is along the push of astronaut 1 or something, right? So set your coordinate system. Think about breaking things into components. And then you can think about applying Newton's second law to each of those, either the x or the y. Kind of like you did for kinematics. All right, so back to this question again. So we're still working toward finding the magnitude and direction of the satellite's acceleration. Now the question is, what is the direction of the net force from the two astronauts relative to the force of the first? So if you set up your coordinate system to say x is along the direction of the first push, right, the first astronaut that's pushing, I want to know what's the direction of the net force relative to the positive x. So I know this is forces and that's kind of new, but vectors is something you've seen, right? So kind of get rid of the word force and just put in vector, right? And I want to know what is the direction of the sum of these two, right? Because we decided, yeah.
So like with the force, like 41 newtons, like is that the magnitude of the vector?
Yes.
Okay, so that's kind of like substitute as a distance.
Yeah, exactly.
Okay.
Yeah, it just has a different unit.
Okay.
Very good.
Well, we know how to do that.
Good. Good. So yeah, it sounds foreign, but you know how to do this process.
Interesting. You're right. I did not do that. There it is.
Kind of components of the mission vectors, plus the probably 6 newtons and the 41 newtons and then all this together. It's all you know how hard it is.
just so people could check. And it has some pictures. Here, the I-hat just says, this component is my X.
You know, the 51 is the function.
Oh, I added these two?
That doesn't.
Does it not equal 51? Could be my math skills.
No, I
Let's
got
see.
51.
I did 41 cosine of 52,
Oh, see,
which is
here.
25,
Yeah, I know it's 51.
plus 26.
I got it. Okay.
Yes.
How do we go from your I hat and J hat to get the angle?
Oh, good question. Does anyone know?
We get an angle for I hat,
How do we get it?
papers.
Tangent inverse. So you could draw a little picture for yourself, right? So I could draw what F net looks like. So F net is 51 in the I hat, right? So we'll say that's 51, right? 51, and then it's 32, so kind of like half-ish, right? So 32. So it looks something like this. And this is, this is the direction of the original push, because I said it was in the X, right? So this is the angle I'm worried about. So this side of my triangle, right, and this side of my triangle are just my X and Y components, my little I hat and J hat coefficients, right? So here's my 51.24 newtons. This one is 32.31 newtons. And then, just as Ben said, tangent will help you get that, right? So tangent of theta is the opposite over adjacent for newtons, and then inverse tangent. Any other questions on this? All right, so yeah, it has some foreign words in here, but it's the same process that you've seen. Hopefully this looks very, very, very familiar at some level, right? Kind of like a... All right. Next question. What is the magnitude of the net force from the two astronauts? So we found the direction of the force. I want to know what's the magnitude of the force. Seeing a lot of agreement. I don't remember the answer, but I'm seeing a lot of agreement, so I'm guessing that either you're all wrong or you're all right. Yeah, I see head nods, good. Yay. Okay, so just to be explicit, how did you get the magnitude? Pythagorean theorem. These are the two side legs, right? Square them, add them, take the square root of that sum. Excellent. All right, now, this is a little bit new. I want to know, what is the magnitude of the satellite's acceleration? So we just found, keep in mind, so I'm stepping you through it, right? So use the hints I've been leading you up with. We just found the magnitude and the direction of the satellite's force. We're in a subject on Newton's laws. Go back to what you were done for the quiz. We're in Newton's laws, so this is the new equation. Yeah. Yes, Caitlin?
What does mass have to be like?
It's the kilograms. That's the unit of mass. I don't remember that answer. But you look like someone agrees with you, so I'm really confident in this calculator skills. Is anyone feeling rusty on the answer, what is Newton's second law? So this symbol is just a sum, so it's like adding forces, right? Equals a constant times the acceleration. So the acceleration should have the same direction as the force, because this is just a scalar multiplying by it, right? So it just stretches or squishes, it can't change direction. So then this sum of forces has to have the same direction as the acceleration vector. And their magnitude is related by the mass. You did your first Newton's second law problem. It's not so bad, right? It's not so bad.
Can't wait for a second.
You can't wait for the second one. That's the spirit, Marty. Okay, so here's another one. So we have Jack and Jill that are lifting up a pail of water, with Jack exerting a force of 7 newtons and Jill exerting a force of 11 newtons. Go Jill. 28 degrees to the right of vertical. At what angle should Jack exert his force for the pail to accelerate straight upwards? So draw a picture of it. I know the picture's here, but draw a picture. And then try to do your own free body diagram. So draw your picture, just whatever comes to mind. And then to draw that free body diagram where the whole pail is a single point, and the forces acting on it are vectors with their tails sitting on that dot. Since we're getting a little close to time, let's talk through this together. Because this one's a little weird, and I should have broken it down more. But you want to split, okay, so do you have a picture? Free body diagram looks something like this. Okay, we're all on the same page there. Good. That's sometimes the hardest part of the battle. Now you want to split this into x and y components, right? They're still vectors, right? Even though they have weird units. Still vectors. We want to break them into x and y components. So how many of these vectors have x components to them? Non-zero x components.
For sure, Jill.
For sure, Jill. And
Just the resultant's gonna have a 0x component.
right, the resultant, right? So, and this gravity has a 0x component, right? Because it's going straight down. So if we say that, assuming, these are my coordinate system, right? That one doesn't have one. So we know that the sum of the forces in the x direction has to equal 0 for our resultant, right? And then, so we write down all the forces that have their x components, right, and add them up, and they should be 0. So the force of Jack, right, his x component, plus the force of Jill's x component should equal 0, right? And then we can use a little bit of, trig to kind of help us with some of this, right? So we don't know what the angle for Jack is. We could say it's some theta, right? And we know that the force, so we have the magnitude of Jack's force, which is 7. Yeah, okay, so Jack has 7 newtons. Cosine of, oh wait, sorry. It's going to be sine of theta, right? Because I want, what is this component, right? The x component, so it's the opposite side. So even though it's your x component, we're using sine. Okay? Just kind of, I want to know what's this, this piece, this component of Jack's. So it's going to be the magnitude of his force times sine of what angle he's pulling at. And I'm going to say it's negative because it's a negative x. And then Jill's force is going to be the positive x, and she pulls with 11 newtons, and it's going to be sine of 28 degrees. And that whole, this sum of the forces in the x is going to be equal to 0. So now you'll notice I just have one unknown, and it's the angle that Jack is pulling at. So you could solve for it.
Oh, so you did it like that. I did it and I essentially got the same thing. But
Okay.
I did it so I found Jill's x and y components.
Yeah.
And then her x component was 5.2, so then I knew that Jack's x component would have to equal negative 5.2.
Mhm.
So then I just did that. And I found
Yep, you did the same thing, just in a different order.
Okay.
So this number should be that 5.2, right? So, you're saying that in order for it not to accelerate in the x, the forces need to be equal and opposite,
Yeah.
right?
Yeah.
Which is Newton's third law. So these laws are very related.
Yeah.
But if you just take your equation that you used and add, so they're both on the same side, it'll be force of Jill in the x plus force of Jack in the x equals 0.
Okay.
Instead of
So
force
that's
of Jill equals minus force of Jack.
That's the third law.
Is equal and opposite, right? So it would be at rest in that x direction, right? So then.
Yeah.
Equal and opposite.
High school was a bell and
Right. All right, but we are out of time. So again, if you have trouble, kind of visualizing that airplane problem.